Right, thank you. I don't know what to say, good morning or good day or good evening, because I think you're all over. But good day summarizes everything. Thank you for joining this webinar. Before I start, I would just like to say that none of the ideas that I'll be talking about are mine, the general ones. But I usually work with the thinking that I don't need to know everything. I just need to know where to find it, where I need it. That's also not mine. This is Albert Einstein's. The things that people like us that work with depend on the statement that Isaac Newton wrote in 1675. This is a statement that means a lot to me, actually, because it was my first report that I was asked to write for a course I took N years ago on my first steps towards reforming my own teaching. If I have ever seen further, it is by standing on the shoulders of giants. And that means that he had been able to discover more about the universe than others. Then it was because he was working in the light of discoveries made by scientists, either in his own time or earlier than that. In preparation for our new series, focusing on the new 2020 MYP guide, we find ourselves in a world where the machines are programmed to do the mathematics and wonder, what do mathematicians do? As applied to teachers, this translates into, when the students use technology to do the mathematics, then what do teachers do? The response is actually simple and straightforward. Our historical role as educators has not changed. We still help the students actually get the knowledge that we want. But the emphasis is now evidently on selection and interpretation rather than manipulation and procedures. As teachers, we feel the necessity for a major shift in the instructional methods we employ. Impart mathematical knowledge to our students. And I'm not hinting that this happens overnight, though. It will take years. And I speak here from experience, going through that myself. Nothing that I'm suggesting I have not really done in my teaching. Actually, before I started thinking of reforming my teaching, I was about to leave the profession itself. But thank God I stayed the course, had patience, and did the change. I'm almost sure that everyone that joined us is on the way of changing this, so I don't need to lecture you about it. The impression that math ability is fixed is a significant part of the reason that math anxiety is so common. Many children grow up thinking that either you can do math or you can't. And when they struggle, they assume that they can't. And from that point on, any struggle is a further reminder of their alleged shortcomings. This affects millions of people. And as I read, actually, it's about 50% of all young adults in the workforce have math anxiety. And of course, this differs from one country to the other. Some countries have more than 50% and some have less. As I said, I'm going to be using some quotes from the giants, and this is one of them that is recent. And this is from Jo Boaler, if you've heard of her. It is hard to know how many people walk around in society harboring damaging ideas about their math ability. But I estimate to be at least half of the population. Researchers now know that when people with math anxiety encounter numbers, a fear center in the brain is activated, and the same fear center that lights up when people see snakes. Well, that's pretty bad news. So still quoting her, what is mathematics really, and why do so many students either hate it or fear it, or both? Mathematics is different from other subjects, not because it is right or wrong, as many people would say, but because it is taught in ways that are not used by other subject teachers. And people hold beliefs about mathematics that they do not hold about other subjects. One way that mathematics is different is that it is often thought of as a performance subject. If you ask most students what they think their role is in math classrooms, they tell you it is to get questions right. Students rarely think that they are in a math classroom to appreciate the beauty of mathematics or ask deep questions, to explore the rich set of connections that make up the subject, or even to learn about applicability of that subject. They think they are in the math classroom just to perform. Well, English teachers do not teach to make every student a poet. If they do it well, then students grow to appreciate poetry. Science teachers do not teach to make every student a scientist. Students grow to appreciate the role of science has in our lives. Art teachers do not teach to make every student a musician or a painter. Students grow to appreciate music and art and other things, of course. So should we in math. We must not try to make every student a mathematician. God forbid, imagine that everybody in the world is a mathematician. We need our students to see the subject without fear, appreciate its power, beauty, and usefulness. This is what we have to do. Luckily, the IB, in working on the guide, did look at recent research and so on. Let's take a look at excerpts from the MYP guide that demonstrate the congruence between our series philosophy, which you'll hopefully see if you end up getting samples of it, and what the IB expect. Sometimes it may sound even as a repetition, or one of us is copying the other, not to be very arrogant. This is because, rightly so, this time, the IB's work in the MYP guide appears to have followed recent research on mathematical education, a very welcome development. So did we. Even though I have worked in an IB environment since 1977, I was frequently skeptical of what the organization produced. Now I have to admit, they really did it right this time. Well, let's look at the aims as given in the guide. I'm sure it's not very far from there. It says, I think it is on page 7. The aims of the mathematics in the MYP are to encourage and enable the students, and just focus on the encourage and enable. Actually, we don't want to force anyone into doing anything. Enjoy the mathematics, develop curiosity, and begin to appreciate its elegance and power. Develop an understanding of the principle and nature of mathematics. This has been done all over the years. This is not new, but it is there. Communicate clearly and confidentially in a variety of contexts. And I think you agree with me that this has been a problem in our classrooms. Every assessment you give, every homework you give, etc., you get a bunch of calculations that the students produce, and in the end, some kind of an answer, which when you go over the homework, they discover that it is right or wrong. The communicating of ideas and so on has to be focused on. This is one of the shifts that we're talking about. Develop logical, critical, and creative thinking. This goes along towards the problem-solving activities. Develop confidence, perseverance, and independence in mathematical thinking and problem-solving. And that's the thing that rings very well in my ears, that they are really focusing on problem-solving. Develop powers of generalization and abstraction. Apply and transfer skills to a wide range of real-life situations, other areas of knowledge and future developments. And that would be the applications orientation that you see either in the MYP now or the DP. Appreciate how development in technology and mathematics have influenced each other. And that I think we just started with, and you will see all over the books. Develop the ability to reflect critically upon their own work and the work of others. And just pay attention to the work of others. This is quite important because it is an indication to later on focusing on group work that helps the work and understanding a lot, and that we focus on in our books too. I forgot to say that the first time I'm exposed to making a difference between aims and objectives was when looking at the IB guides, whether in the DP or in the MYP now. I used to use them interchangeably, but the aim is what we hope to achieve, and the objective is something that is measurable by a test or some other assessment criteria, but it is the actions that we take in order to achieve that aim. Now, the next thing that we look at would be the objectives that they mention. Knowing and understanding. Of course, knowledge and understanding are fundamental to studying mathematics and form the base from which to explore concepts and develop the skills. And for them, in order to reach the aims of the mathematics, students should be able to select appropriate mathematics when solving problems in both familiar and unfamiliar situations. Familiar situations means that when you give an example or when they work on an exploration that explains some concept, that would be familiar to them. Unfamiliar would be in a later activity, whether it is an assessment or a homework or just reading something, etc. It would be an application of that familiar situation that they haven't seen before. And I'm sure that you've heard a lot of complaints sometimes from your students when you give a test that, oh, we haven't done that in class. But that should not be the case. They really need to learn the math and be able to apply it in unfamiliar situation. Apply the selected mathematics successfully when solving problems and solve the problems correctly in a variety of contexts. More or less all go hand in hand. Investigating patterns. This is a good activity that is given. Working through investigations encourages students to become risk takers. They can guess, they can inquire, they can become critical thinkers, and so on. In order to reach these aims, the student should be able to select and apply mathematical problem-solving techniques to discover complex patterns. We have enough advice in the book and in the guides. Here I could mention that every book comes with a teacher guide. This is a must because of our approach. There is a lot of information that is given to the teacher in terms of how to set up the class atmosphere so that the students could maximize their benefit from using the books themselves. Describe patterns as general rules considered consistent with findings, which means that step by step students would be brought up to this understanding, and they draw their own conclusions. And this is a translation of what we mean, that they are becoming partners in the learning process, not only receivers. Prove or verify and justify general rules. Perhaps prove is a little bit very ambitious right at the beginning of the MYP program, but towards the end, this is something to be expected. Most of the ideas are either verified or justified in working, so that they really feel that or feel comfortable at what they arrived at. We talked a little bit about the communicating. It is, even though it is communicating and has nothing to do with the symbolic manipulation that we are used to, but communicating what you learn is a very important thing in the mathematics learning. And in order to reach these aims or these objectives, students should be able to use appropriate mathematical language, notation, symbols, and terminology in both oral and written explanation. I just give you an example that people always talk about congruence. Like if you talk about congruent segments or equal, and students should be able to know that one of them is used correctly and the other one really loosely used. The segments could be congruent, and they have to know that. If they are congruent, then they have the same measure. And equal, they can only be equal if they are the same line segment, because to be equal from the set theory means that they have to be made up of the same points. Use appropriate forms of mathematical representation to present information, either by a formula, by a graph, and move between different forms of these representation is something that they have to get used to. Communicate complete, coherent, and concise mathematical lines of reasoning. That, as I mentioned, you just don't get a bunch of calculations and there you go, here's the answer. The last thing that they talk about in the objectives would be applying the mathematics in real life context. And this one deals with the learning of where they can apply the mathematics. We put enough real life applications of the mathematics in the books, starting from year one, really. And in order to reach these aims, the students should be able to identify relative elements of authentic real life situations, select appropriate mathematical strategies when solving these real life situations, apply the strategies successfully to reach a solution. You have seen a lot of these models of applied problems where the student manages, or whoever is doing the application problem, you get from the real life situation, transform it into a mathematical model, come up with the solution to the model, then test the model. If the model works, okay, then you go back and you check it to see whether it makes sense in the context of the problem, etc. If it is acceptable, then you take it. Otherwise, you have to restart this cycle of applied mathematics. And that's what they are really asking for. Now to our series. For a year by now, when we just started working on the series, this was a real challenge given the usual late, I mean, I can't avoid criticizing the IB a little bit, the late official release of the new guide. Like they release it and then within a very short period of time, you have to be able to write books for it. But we were lucky finding or working with 12 enthusiastic and experienced teachers from the international schools community. And this was a very, very rich and rewarding and learning experience. In the series, we focused on three main ideas. Of course, these ideas are not completely ours. They're depending on research done by mathematical education researchers. I'm almost sure that you know that we have a tendency that if you are in class and you get a question, then there you go. You throw the answer because you're the source of information and so on. Perhaps that's the first thing that we may to accept to change a little bit. And as Bowler says, a time for telling. The question is not should we tell or explain the methods, but when it is the best time to do this. And the best time is after the students has explored the problem first. And the principle that we use is that the delivery of the concepts follows this research and how students learn. So first, they need to explore new ideas first before they are being told. And as Van Heele, I don't know whether you heard of them or not, the Dina and Pierre Van Heele are the ones who developed the steps of geometric principles learning. They have 5 levels of it. I'm not going to be talking about it, but I'm sure that you can Google it and research it if you haven't seen it before. A definition of a concept is only possible if one already knows to some extent the thing that is to be defined. I will go through some examples that we have in the book so that you could see how we are really applying this. The main basic idea that we have in the books is what we call explore. And we tried very hard from book 1, as I said, that any new concept the students are going to be discovering, they have to explore first. They would be given a situation and they should come up with the ideas. This goes hand in hand with the group work that I'm talking about. They should be in small groups. They work independently and in the groups, exchange ideas, and try to come up with the principle that we want. Here's an example. This is an activity, which is an explore, as we said, that is meant to refresh students' knowledge of vertically opposite angles and adjacent angles, supplementary angles, and so on. Just one piece of information where they can really get the rest of it. And that's the only question we ask. And here, this is where the need for the guide is that the teacher is given some suggestions. I don't want to say instructions because that's not really helpful. Suggestions of how to run this explore. The students should be given some time to stare at the problem, that's fine, to make guesses, make mistakes. And by the way, the mistakes, you would want them not to expose the student that made them, but to try to have the students learn from their own mistakes. This is something we always say. I mean, as a parent, I always said that to my children. So another example. We want to refresh their memory about the relationships of the angles when 2 parallel lines are intersected by a transversal. you could imagine how many conclusions the student can really come up with this. And in a small group, for example, then that would be a very rich discussion. And when the teacher tries to bring about a whole class discussion of the whole thing, you can imagine how many ideas, right or wrong, can come up, and how much the students would be learning from it. Of course, here the students discover the concepts, put in correct form after the class discussion with the teacher, and they would eventually do an investigation to try to confirm most of these results. Here's another example which conveys the method I'm talking about a little bit further. Of course, there are several instances of real-life applications, and this would be an exploration. You notice it's in the same chapter, that the students want to discover the sum of the interior angles of a polygon, convex polygon. So we start with the quadrilateral. They can make the connection that quadrilateral has 4 sides, but 2 such triangles. Pentagon, 5, 3 triangles. They can try the hexagon if they want to, etc. But in the end, we ask them to guess what it is with the n triangles, with the n-sided polygon. And we don't really ask, we avoid as much as possible to ask questions that are direct. Just always probing. Can you find this? If you can't, try to investigate it more, discuss with a partner in the group and so on, but we want you to come up with the conclusion yourself. That doesn't mean we don't tell you, and that's where I'm just going to be sharing a little bit later with you. All these discoveries are actually confirmed by an investigation that comes afterwards. And that investigation is not a repetition, but it is looking at the problem from a different angle, as you see here. And by more or less leading them to the correct conclusion in the end, generalizing the whole thing, a few pages afterwards, the facts appear either on a margin note or in a note that is in the text itself. And this is what we wanted them to find, that the sum of the interior angles of an n-sided polygon can be found using the formula, which hopefully, and I think that you will agree with me, is not going to be new to them because they have discovered it. There is, of course, an activity for the exterior angles that they can also confirm with the result that would be given there. The second idea that we focus on would be on problem solving. And the father of problem solving should not be forgotten here. Actually, it was my first step towards discovering how wrong I was in my teaching before I got exposed to the book by Polya on how to solve it. And Polya says, the first and foremost duty of the high school in teaching mathematics is to emphasize methodical work in problem solving. The teacher who wishes to serve equally all his students should teach problem solving so that it is about 1/3 mathematics and 2/3 common sense. He is rightly so considered to be the father of problem solving, and everybody up till now in my humble opinion, still repeating what Polya actually established. He established the heuristics of problem solving, and we are actually following here. Just a word about problem solving, that he was not the one who invented the whole thing. Problem solving has been in discussion before. It passed through kind of three phases. The problem solving as a context, which is based on the idea that problem solving is a method used to accomplish other ends like justification, recreation, and so on. And I'm sure that in literature you find hundreds of books about it. The problem solving as a skill, which distinguishes between solving routine and non-routine questions. Also, there are plenty of activities and books written about it. But problem solving as an art, this is the view that emerged from his work. And he revived the idea of heuristic. And the heuristic is the art of discovery. And he asked, how did people make mathematical discoveries? Answering the question led him to conclude that students understand mathematics better if they see how it was created in the first place. And if they can get some taste of mathematical discovery themselves, he argued that the finished phase of mathematics, usually presented deductively in textbooks, does not do justice at all to the subject. Finished mathematics requires demonstrative reasoning, whereas the mathematics in the making requires plausible reasoning. And if students are used to plausible reasoning, they need to be taught how. The explanation in detail is actually given in the guide to the teacher who did not do the reading or doesn't want to do it. Now we come to Polya's 4 steps problem solving. If you haven't seen it, of course, many of you will say this is obvious, but I can ask you one question in a minute. So the first thing is understand the problem. We're using some abbreviation for them. Then make a plan or devise a plan, carry out the plan, and look back. I can ask you to think. Unfortunately, we're not going to be able to communicate back and forth here. Where do you think the students will start seeing a problem? To make it easy for you, and that's my experience also, they start here at step 3. They carry out a plan that they did not make. And in many cases, they get stuck because there is no plan. They just know the symbolic manipulation and they give up. That math is not for me. We want them to understand the problem. So what does it mean understanding the problem itself? Where should I start? Start from the statement of the problem. What can I do? Visualize the problem as a whole, as clearly and as vividly as you can. What can I gain by doing so? You will see, I'll give you an example about what you can get from that. And the suggestions would be read the problem so that you understand it. Reread it a second time, and perhaps a third time and a fourth time. Can you restate the problem in your own words? And this is very important, really. Even Einstein says, if you cannot explain it simply, then you don't understand it well enough. So try to restate it, especially if it's a non-standard or non-familiar situation itself. Can you determine what you're looking for? What is the unknown? What facts are given? How should it look like? What conditions must be satisfied, etc., etc. And the list would be quite long. And that's what I'm saying. It would be a long list and some practice. You cannot get this overnight, neither yourself nor with your students. They have to get used to this system. At the beginning of my transformation and so on, and when I adopted this method, etc., every year at the beginning of the year, I had plenty of headaches from students and from parents. This guy doesn't really answer questions, because every time a student comes, I answer a question by posing another question that they have to really come up with it themselves. But in the end, they get used to the system, and I think many of them, even the ones that we don't call good students, were still in touch and are still in touch. The second thing would be to devise a plan. The results of the mathematician's creative work is demonstrative reasoning, a proof, but the proof is discovered by plausible reasoning and by guessing. Many of us have kind of reluctancy against guessing, but guessing is a very important steps. And as you see, I put a statement for Newton here. No great discovery can ever or was ever made without a bold guess. You look and you look, and it's, of course, it's not only a lucky guess. Of course, you observe, you explore, and so on, and then you can take your guess. And the guess is not enough, of course. You have to confirm it afterwards. Have you ever seen the problem or one substantial similar to it? Can you find a pattern or relationship? Do you know of a related problem? Is there a theorem that you know that you could use, and so on? So those things also, we are reminded by Einstein's statement that I don't need to know everything. I just need to know where to find it when I need it. Can you restate the problem differently? Work backwards. Identify a sub-goal if the final goal is not really clear to you, and so on. The third step, and that's where the students usually go, is carrying out the plan. And carrying out the plan is not only doing the symbolic manipulation, but you have to be patient, and you have to keep record of your work. And again, copying Newton, if I ever made any valuable discoveries, it has been due more to patient attention than any other talent. Check each step of the plan, and as you proceed, this may be initiative to checking of a formal proof of each step, etc. And again, we look at what Einstein said. It's not that I am so smart, it is just that I stay with the problem longer. And the students should get used to keeping an accurate record of their work. The last step would be looking back, and many people, including us, finish. Once you find the solution, you don't do anything anymore. And here it says, as Polya says, even fairly good students, when they have obtained the solution of the problem and written down neatly the argument, shut their books and look for something else. And as he said, you have to check the results in the original problem. In some cases, this would require a proof. Interpret the solution, whether it makes sense or doesn't make sense. That's why you don't get, if students are doing it right, you don't get a probability of minus 0.5 or something like that. And many times, and I think you know that from your own experience, yes, true, you find the solution to a problem, but then after finding the solution to the problem, you look at it and you see that, well, this is not the most elegant solution that I can find. No, there is a better way of doing it. Or not even that, you can actually look at extending it somewhere else. It is a very rich experience. I have I had gone through this thing really myself. Sometimes I was asked to find the locus or vertices of a parabola y equals ax squared plus bx plus c as the coefficient of x squared changes, is used as a parameter, while bx and c are fixed. And I think you know this exercise. It is in the literature all over. The locus of the vertex would be a straight line, which you can find. It's the bx plus c, or minus bx plus c, I forgot it now. But looking back, I thought, well, what about if we can extend it to the cubic polynomial? Is there something like that? And the thing is, yes, there is. If you have ax cubed plus bx squared plus cx plus d, and if you vary the coefficient of the x cubed, you're going to get the locus of both vertices, if they exist or when they exist. They move along a parabola that you can predict. If you, well, anyway, let's cut the long story short, but it's always fun and rich experience if you look back, at least to see if it makes sense or it does not make sense. We have plenty of instances where we show the students how to use Polia's steps, and in book 1, chapter 2, we actually give them a whole list of strategies that they can follow. Let's look at some of the examples, but before that, the list of strategies. So we introduced those ones: trial and improvement, changing the name from the negative trial and error to trial and improvement, making a list, making a table, eliminate possibilities, make a diagram. I'm sure you can come up with things that are that can be added to our list here. Here's an example. Construct a parallelogram with the lengths of the two segments that are given here. If you recall, we said that in trying to understand the problem, draw a sketch, see what it could mean, and so on. And in construction problems, I don't think that you need me to lecture you about. You need to know how it may look like towards the end. And that's why we have something that looks like a hand-drawn diagram. And since there is no mention of any angles, etc., therefore, as you notice, it will boil down to drawing two sides of the parallelogram and then finishing it. And here you need to remember a couple of things. As you notice that this is from a chapter where they are familiar with the idea of locus also, and the properties of parallelograms. And since you are given the length of two sides, therefore, in their plan, they could use the fact that the opposite sides of a parallelogram are congruent. Remember, not equal. So carrying out the plan uses the concept of the locus, and that is, as we said, applying the steps of or the heuristics of Polya. But here I just want to mention it in case I forget to mention it afterwards. We don't want to make the whole thing mechanical. So in every chapter, the steps for the heuristics are called what they are: understand the problem, make a plan, carry out the plan, etc. But in the rest of the examples, they don't have to be mechanical and start filling it like a worksheet and so on. So we show them that we are following the plan, but without really just calling the names themselves. And of course, what is missing still would be the looking back, and we ask them to look back. And to confirm looking back and try to give opportunities to extend it beyond this one, every worked example and every explore sometimes, or most of the explores, are followed by a window for the student to reflect on what they have done. This reflection is very important, actually, not only in problem solving. I think in teaching, I used to have this habit that at the end of the day, I sit down and have a reflection of what I did. To be honest with you, which you expect that, of course, that did not start early. Only when I thought that I have to change so that I can enjoy what I'm doing. And by reflection, you always see where you went right, where you went wrong, and then you can fix it the next day. So I'm not going to bore you with many examples. I just put them here for the fact of putting them, showing you that this is from a different book. I think this is book 3 and a later chapter using statistics. And we also go through the polio steps so that the student makes the most out of it. This is a little bit more extensive. Reflection is there. The use of technology is also there for students to do. I think I overdid it in these examples, so I think that, as Catherine said, you may get a copy of it. Now, other than problem solving, the third thing that we are focusing on, the idea, would be to allow the students to work in groups. The IB mentions this, and all the research mentions this. The collaborative group work is very helpful tool in changing students from passive receivers of information into partners in the learning process. This is borrowed from NCTM. Mathematical discourse among students is central to meaningful learning of mathematics. The benefits of small groups, however, depend on the quality of the student-to-student discourse. If students do not engage with one another, they do not have the opportunities to share ideas, evaluate the reasoning of others, and build understanding. And this is where, as I said, in the guide that comes with the book, there are a lot of suggestions of how you can do that. We will discuss it a little bit later. But also, let's just take a look at what the IB says in this respect. And this is what I really respect, that they went through this, that the IB learner profile, they want inquirers. I just chose some of them that go in this direction. We know how to learn independently and with others. Communicators, we collaborate effectively, listening carefully to the perspective of other individuals and groups. And in the group work that we're suggesting, we encourage people to rephrase other students' statements also, to show respect and understanding of what the others are saying. Risk takers, they work independently and cooperatively to explore new ideas, make guesses, try to support their guesses, and so on. And that is something that we appreciate a lot in this work. As I said, in the group work, we bank on mistakes that happen because people have to learn from their mistakes, and they could make a mistake more than once. Don't we make mistakes when we're solving problems? And as Nelson Mandela says, do not judge me by my success, judge me by how many times I fell down and got back up again. And that's what really the students should be doing. So this is also adapted from NCTM. What you should be doing, in their opinion, I'm not saying that this is a dictation on you. Engage students in purposes sharing of mathematical ideas, reasoning, and approaches using varied representations, which means that your students would be presenting, explaining ideas, reasoning and representation to one another in pair, in small group, and the whole class scores. The whole class scores is chosen by you. It doesn't have to be a student doing it. In my years of teaching the IB diploma and in preparation for exams, I did not really review for the students. I had the arrangement that the groups themselves, on a chosen day for them, they prepare a lot and they review together. And that means that every group would have a day where they take control of reviewing for the whole class a certain year of exams, explain the problems, answer questions, even preparing quizzes for their classmates, etc. So facilitating discourse among students by positioning them as authors of ideas who explain and defend their approaches. This is very important, that the students need to feel that they own the idea that they brought about, and that they're not really repeating what you as a teacher gave them as information and so on. You should help them discover, but they shouldn't always think that the only source of information is from that source. We're kind of running out of time, but you will get this document. At the end of every chapter, I think you know from textbooks, you have a summary, and the summary is written by the author of the chapter. And of course, if I'm the author of the chapter, I summarize what I wrote. What is the benefit of the student, for the student? What we showed here would be this self-assessment. It's like a checklist where the student, with the help of the teacher and so on, could go through this one. And the teacher should give advice to the students, is that any place where you are not sure that you can really put a check in the list, go back and try to see what is you're missing. So we are not really doing the summary. Instead, we have this for you. Of course, at the end of every chapter, we have check your knowledge problems, which is like review problems, where you look at the whole chapter or as a whole unit, and they are direct, not very difficult, but direct to check the understanding of the question. I use many references when I work. I mentioned some of them here for you, so you can take a look at them. And if you haven't read George Polya yet, don't feel bad, but you should be really doing it, especially him. And Joe Bowler is a new one. At least she's still alive, not like Polya. In the end, if you have any questions, you can ask them. But if you want to get in touch with me for any questions you have, I always check my inbox, so I will answer you within a short period of time. If you want to, this is my contact, or join my LinkedIn network. I don't know how to tell you how to do it, but I'm sure that if you are in LinkedIn, you can find me. Thank you. Now to answering question, if Catherine.
Yeah, thanks, Ibrahim. So a couple of questions have come through already. So somebody's asking, how do you feel about assessing several criteria at the same time?
Sorry, can you repeat that?
How do you feel about assessing several criteria at the same time? I think the assessment criteria, you assessing several of them at the same time.
Well, this is fine. I mean, if whatever the students learn and can demonstrate an understanding of what you are targeting, then that would be fine. It doesn't have to be specialized so that the student knows or expects that, okay, I'm being evaluated on this criteria now. I hope I understood the question right to
I think so.
answer. Yeah.
And then there's another question that I can answer actually. So are the key concepts and related concepts and global context suggested on each chapter? So yes, for each chapter, we've listed a key concept, related concepts, global context, and also a statement of inquiry and inquiry questions.
The teacher guides also contain plenty of material for the teacher. This is why I'm saying that it is a must that the guide should be with the teacher. It's in electronic form only, I think, right, Catherine?
Yes.
Yeah. So there's a unit plan that explains everything that is connected with the official things, the criteria and the goals and the explores and the investigations and the questions and so on. And the chapter will, there would be an overview of the chapter. There would be a look at the prerequisites that are needed there. There would be quiz questions that help the teacher open or close the class by asking these questions to check the prerequisite material. And there are text questions because we are of the belief that the student needs to read the chapter. And the text questions would be questions to check whether they read it or they did not read it, which means that these would be given at the beginning of the class. We suggest some time and emphasis on what you do. Like if the students are reading the book, then that doesn't mean that you have to go over every single item in the chapter. And the number of problems that are in the book itself, due to limit of size of the book, etc. Perhaps you don't find enough. We give you some extra practice questions that you can choose from. And these would be of two types. One is the extra practice questions that are similar to the book's question, but they're not in there. And then challenge, which would be assigned to teachers that would really like the challenge. And then for class discussion, we give you some material for groups and so on that are not in the book itself, but they'll give it to you to work on. The Explore investigation, you have enough suggestions on what to do there and how you can run it.
So we do have one question just come in. Will there be assessments in the teacher guide?
Sorry?
Will there be assessments in the teacher guide?
We have in the teacher guide, I think you can answer that. We have the plans. We have actually, one second, I'm just looking at what we have because it's a long list. We have the unit plans. We give an overview of every chapter. We check the prerequisites for everyone, and we give quiz questions that address these prerequisites. We want the students to read the chapters before coming to class. Therefore, we have text questions that are addressing what they have covered. We suggest the time and emphasis for that they need to spend, the teachers need to spend, the points to stress, and then we give extra practice questions, and these could be used by the teacher to have some assessment. And we also give some challenge questions in case you have students that are not really challenged by the questions that are in the textbook. You will be given some material to go with it, and an extra materials for class discussion if whatever happens in the chapters would also be there. the group work and so on I talked about. So assessment per se like this, I don't know, we need to have some kind of answer from you.
Okay, Ibrahim and I will discuss that and follow up with you. So another question that's come in is how would
here, may I interrupt?
Yes.
There is some kind of basic principle in terms of the assessment, because the new theories do not really stress too much giving tests and grades and so on, because students are very much discouraged normally by seeing an F on their test, for example, and so on. So assessment can come up from the teacher experience himself or herself in class, so that they could see whether the students got whatever is in the chapter, and give them some feedback in what is needed to be done to fix any errors that can happen, and to more or less encourage them what they did correctly. Okay, sorry to interrupt you.
That's okay. So the question I was reading was, how would a school deal with series if the scope and if the school's scope and sequence is different from that of the series?
Well, are they teaching the MYP or they're not teaching the MYP? That I don't know, but the chapters actually could be more or less as standalone chapters where the teacher can control it. Different from other books that are for the MYP. You still look at the topics you want to, and you actually choose the chapter that you want to teach. So I don't want to talk about the competitors here, but you definitely know if you want to talk about arithmetic sequences, you find arithmetic sequences. If you want to talk about similar triangles, you find similar triangles. You don't have to look for the whole book to do it. So even if the school plans are slightly different, they can actually use the books.
Thank you. Another question, what does unfamiliar situations really mean as compared to familiar situations in the criterion A?
A familiar situation would be when you give something, since we're talking about arithmetic sequences, for example, therefore you have a problem on arithmetic sequences, and the students know how to deal with an arithmetic sequence. The unfamiliar situation, even if it has not been done in class, but in an assessment, a question concerning arithmetic sequences in an applied situation can come up, and the student has to use what she or he has learned so that they can deal with that problem. That's what we mean by the unfamiliarity.
Okay, and there's been a couple of questions about the transition to DP. So Timothy asks, what about transition from MYP5 to DP? And then somebody else has asked, does the series provide extended and standard options in 4 and 5? And if so, please elaborate, especially regarding the transition from MYP to DP.
The students are not going to feel there is a transition between the MYP 4-5 and the DP. It is actually the same approach, and there is so much overlap sometimes between what topics are dealt with in the DP 1 books or the beginning books of the higher level or the standard level, and the MYP 4-5, especially for those that are going to higher level. For example, they're going to find our extended book 4-5 is a very good introduction to the DP books. That is definitely the case.
Thank you. So we've actually run out of time. If you asked a question and we didn't answer it, we will be doing an FAQ document that we will send out with the email and the recording. So please do keep an eye out for that. And thank you again, everybody, for joining. And thank you, Ibrahim, for presenting.
You're welcome. My pleasure. And if anyone really needs to communicate with me, the email I always answer. It doesn't sit so much in my inbox.
He does. I can attest to that. Thank you, everybody.
Bye-bye.